Hello Internet! In the last video I showed you about the tensor, how we can construct rank 4 tensors and how we operate with tensors and mathematical operation on tensors. And now I want to ask or answer the question, if we have this complex tensor, a rank 4 tensor with 120 elements, float elements in it, how can we squeeze this tensor into a flat Keras layer? How is this possible if we have a neural network and we have the very first layer? How is it possible to have such a complex mathematical structure like a rank 4 tensor, such a high dimensionality object? How can we squeeze it in a layer? What is going on and what are the mathematical operations in this layer? What is the dimensionality I need in this layer to be able to take the data as an input and perform an operation, a tensor operation on this input data? Or if you want, three simple questions. How does a rank 4 tensor fit into a perceptron? Along what axis is tf.tensordot, the outer product, performed? And how does the dimensionality of a tensor change after a tensor layer operation? And are there limitations given the dimensionality of the different inputs? So let's start at the very beginning. We know one part. We know how the tensor looks like. And here we have a tensor, a rank 4 tensor with 4 axes. And we have 3, 2, 4, and 5 is the shape of our rank 4 tensor. And this has 120 elements, and the elements are float 32. So we have the input data structure. And now we come to the simplest possible layer. What is it? One naked layer. And if you think about it, the simplest layer is actually a perceptron from 1957. It's a simplified model of a biological neuron. And you want to simulate the human neuron in the brain, and this was the idea with the perceptron. Let's build a decision-making machine. And no, we do not want to think about some hidden layers or some advanced complexity. We just look at the very first layer. And there the simplest element is one artificial neuron. And now we have the problem. We have a rank 4 tensor and we have a little red dot as a neuron, and we do not understand what the hell is going on and how can these two mathematical objects perform a tensor operation. So let's dive into this. Let's find the solution and let's see how we can build better layers for our neural network models. At first, we have an artificial neuron. We have an input as a tensor, and the output data will also be a tensor. Now remember, we can have a rank 0 tensor. This is just a scalar, or we might even have a higher ranking tensor as an output. It all depends on the mathematical operation performed in this simplest one artificial neuron. So, 1957, the perceptron. The perceptron was designed as an algorithm for supervised learning. This means we have a labeled data set with a given input and a given output. And the task we want to face is we want to have a binary classifier for a linear hyperplane. So, very easy. Think about you have two regions and a line is separating those two regions. Let's say, I don't know, sunshine and darkness. And there is a boundary line separating the sunshine area from the darkness area. And you want to find exactly the mathematical representation of this hyperplane separating these two segments. On the other hand, you have vectors, you have elements, input vectors, given with numbers, and to represent objects that belong to the sunshine segment, and then you have other data points that go to the darkness segment. And you want to have this linear classifier. And the idea was just to combine the set of weights with the feature vectors. And this is the most important notation you have to remember in this video. The set of weights combined with the feature vectors. And I will show you in a second why this is such an important mathematical construct, because we will see it even in the dense layer structure of Keras. Nothing else. Combine the set of weights that we have, the weight of a link with the feature vector, and this is our input vector. So let's do an example. Let's do a human example, and then we do the mathematical interpretation of this. Imagine I want to attend a party. I'm thinking about it. What are my criteria? I might say, hey, there are nice people to meet, there's great food, maybe there's an open stargazer party afterwards, and it is within walking distance to my flat. So I have defined 4 features that are important for me to decide. And then I check out if this party has a yes or a no condition on each of these green conditions or features. So nice party, nice people to meet. Yes, X is 1, X is yes, there are nice people. And now the importance, the strength of the link here is given in red with a weight. The weight is 0.8. So this is close to 1, means this is very important to me. If it would be a value close to 0, it means it is yes, the function, the condition, but it's not important to me. So very easy. So you go through all the different features. Either you have x equal 1 or x equals 0, where it means no, it's not given. And then you just can calculate the multiplication of each combination of the weights and the feature vectors, and you add it all up. So what we have? First line, x is 1, w is 0.8, so you have 1 times 0.8 plus second line, 1 times 0.7 plus 0 times 0.6 plus last line, 1 times 0.4. And this gives you a numerical value. And now comes the interesting part. A neuron fires only if it's above a certain threshold. Imagine you're sitting at home, at your couch, at your sofa, you're eating chips and you're watching Star Trek. And you say, should I get up? Should I really move my old body and get to this party? This is the threshold value you have to achieve, at least above the threshold value, that you go to the party. So a very easy example. But we will use exactly this reasoning and this mathematical construct to build our artificial neuron, our perceptron. So again, the perceptron inputs are called nodes. Please do not interpret anything into this wording of nodes. And the nodes have, and this is important, a value like x equals 1, yes, or x equals 0, no, and a weight in red. So this is exactly the value that I told you. Yeah, the condition nice people out there is 1, a yes. And the weight indicates, is this a strong link? Is this important for me? And you see, blue is the feature vector and red is the weight matrix will become, or the tensor. So for the next step, I just want to remind you on an equation for non-vertical lines. And we have here the form of the slope-intercept. So we have y equal m times x plus b, where m is the slope of the line, of our separator, of our hyperplane, where we can distinguish the segment of the sunshine from the segment of the darkness. M is the slope or the gradient of the line. So if you want the slope, yeah, of course. B is the y-intercept of the line, so more or less a bias. And x is our independent variable, and x in our case is our feature vector in blue. And so we have a function y equals f of x. Now, a perceptron now is an algorithm for learning a binary classifier called a threshold function. If it's above a certain threshold, as I told you, I go to the party, so we say yes or 1. And if it's otherwise, it is a 0 and I do not go to the party. And no, bool and no, for example. This is your function f of x. And now, to decide if I'm above the threshold, I do exactly the same as I told you. We have the red vector w of our real valued weights. And then I perform the dot product of the weights with the input vector. And this is a dot product where m, our summation we sum over, is the number of inputs to the perceptron. And in our case, I had as m4 criteria for features. And in my case, m would be equal 4. And the input vectors x are often called input feature vector or simply the features. So now we know the notation, now we know the wording, and now we can start with the training because we want to build a model. And for this, we need a labeled data set. So this means we need some data that a model can learn. And we have a labeled data set where we have x is a n-dimensional input vector, and d is the output that we want. The model should learn that d is the correct output. And then you have a lot of training samples. So this is our labeled data set, and then we just do 3 steps. At first, for our model, we just initialize all the weights. So you can either set all the weights to 0, I would not recommend this, set it to a very numerical value. Second, you calculate the actual output and you update the weight for t plus 1. So this means if you start with the weights at t and you have a very, very small numerical value in your weight matrix, you will have the weights now updated to a new numerical value. And as you can see, you have a specific learning rate, whatever it is, .001 or whatever you like. And after a lot of steps, you will notice that the distance between the dj minus the yj at the time step t is becoming smaller and smaller. And it's then sometimes smaller than a user's specified error threshold. And so you can say, okay, the system now trained so much, the error is so small, I'm satisfied, the training is finished. And what have we now? We have now an artificial neuron. And this is the artificial neuron used by the perceptron. So we have on the left side the input data. Our input vector x1 to xn or whatever you like. And you know that the importance of this value of this input is given with the w1. This is the strength, if you want, of the link between those two. And if you do now exactly as you showed you your y equal f of x function, so you calculate x1 times w1 plus x2 times w2 plus, and you do the summation over all of those data, and you do not forget about the bias, then you will come up with a numerical value. And here you see a step function, or a softmax function, or a reload function, or whatever you prefer. And you can now say, okay, am I above or below a certain threshold? It is easy. It's just a binary decision. And if you're above the threshold, you get an output value, let's say yes, and below you get no. So sunshine and darkness or whatever you like. So we have now some model we can train on a labeled data set, and we train the weights. What we are interested in is w1 to wn, because given the activation function here, our softmax function, for example, we have now a nonlinear learning induced to our artificial neuron, and we learn the weights. And the idea is, if we have this model with the trained weights, I have now some new input data, some new data the model has never seen before. The model is able to tell me, hey, this vector belongs to the sunshine segment or it goes down in the darkness. Beautiful. We achieved what we set out to do. We found a mathematical formulation of my artificial neuron of my little red dot. So now we understand that this little red dot is taking an input tensor, performing some mathematical tensor operation, is doing some activation function on this, and outputs a tensor. This is it. So it is a tensor-tensor operation. If you switch now, because you want to calculate this, we are doing this that you can code. You have TensorFlow.keras.input, and you see the first parameter you have to set is the shape of the tensor that you expect as an input. And let's say you have a 32-dimensional vector. A vector, you remember, is a rank 1 tensor. And you say shape equals 32, comma, nothing, parenthesis closed. This indicates that the expected input is batches of a 32-dimensional vector. Beautiful, great. Now, if you want to see the model completely, this is it. Import TensorFlow, import Keras. Then you say, I want to have, let's say, the number of units in this layer, and you want to have, you have an input data of a picture, and the picture has 24 pixels times 24 pixels. So in total, you have 784 pixels per photo, and you have 30 recordings, single pictures per second. So you have an input variable set to 784. Those are your feature vectors. Of course, they constitute a tensor. And then you operate in Keras simply with two elements, with two objects, layers and layers build models. So the first is a model, and we have to define there are two kinds of models, and we do the easy, the sequential model. And then we say we add a layer. And this is our first layer. And of course, our first layer has to have an input, because we can here define as a dense layer an input shape. And this is exactly the number of the pixels that we want to investigate from our vision system. So 784. And then we have a kernel initializer. This, as I told you, the weight matrix should be set to 0 or a very small numerical amount. This is done here. And then you have an activation function. You have to specify a softmax or reload or whatever you like. And beautiful, this is it. And of course, a dense layer, we can have a lot of layers. But the dense layer is a simple layer. And it means also that each neuron in a layer is connected to all neurons located in the previous layer and to all neurons in the following layer. So we have a dense network structure. And if you want to have an abstract mathematical notation, what this layer operation is doing, so we have tf.keras.dense implements a mathematical operation. And it defines the output as, and let's start within the parentheses, a dot product. A dot product you are familiar with of our input vector or input tensor, to be more correct, and our kernel tensor. Now the kernel used to be this red W, the weight matrix I showed you, and this was the significance the good food has to me. It's a W7, for example. And the input was our input feature vectors that I told you, x equals 1 or x equals 0 for all the different features. So we perform a dot operation on tensors. And now we can see why we have this tensor operation, why we were struggling so much with tensor. Because now we are not doing some matrix operation, some vector operation. No, we are in a higher dimensional array. We have a tensor is an n-dimensional array. And now we are finally operating in a higher dimensional space where we have a tensor product. We have a bias, but let's forget about the bias. And then we have an activation function, and this defines our output on a layer level. So the kernel in red, as I told you, a weight matrix created now by the layer, and the bias, forget about this, just shifts the decision boundary. And now for the second question, we can have now an answer. Because it is defined in Keras that if the input to the layer, to the first layer, has a rank, a tensor rank greater than 2, and remember, this is a matrix. Then the dense computes the dot product, but the outer product, the tf.tensordot product along the axis. And now the axes are along the last axis of the input tensor and the first axis, axis 0, of the kernel tensor. And now we know how the tensor multiplication is performed along what axis of what tensors. And this is great because this is already defined for you in Keras. You do not have to take care about this. This is great. Of course, if you then have some hidden layers, you add some hidden layers, and not just input and output layers, but something in the middle, let's call it. You have to switch to some more sophisticated algorithms like backpropagation, gradient descent, and you know everything of this already. But it was important to show you that a layer is a very, very important tensor operation performing some mathematical operation on the input data. It's an input tensor, and the output itself is also a tensor. And it can be whatever layer configuration you like. You can add layer, you can stack layers, you can play around with layers. You have pooling layers, you have dense layers, you have embedding layers, you have convolutional layers. You can define a variety of layers, and I think close to 100 different types of layers are already defined for you in Keras. So you just call the specific layer, and the layer is doing exactly the operation, the mathematical operation you're looking for, and it provides you with the result. This is the beauty of a Keras layer operating on the TensorFlow 2. Keras you can think as a high-level API. TensorFlow 2, if you want, is the low-level API on the Tensor, and it is so beautiful to build your models, to build different layers, to stack layers on top of each other, and to achieve exactly what you set out to do in your task. I hope you enjoyed it a little bit. I brought some insight into the complexity and the dimensionality of higher ranking tensor if you have some layer operation, and how such a complex, mighty beast of a rank 4 tensor fits into a simple, plain Keras layer in TensorFlow 2. I say thank you, and I see you in the next video.